Hello, my name is Jed Murdoch and welcome to Module 11 on Island Biogeography. In this module we'll cover the equilibrium theory of island biogeography, its idea, its concepts, and really some of its predictions. And not only that, but how it relates to conservation biology. Afterwards, a bit later, my colleague Terry will come in and Terry will walk you through and guide you through a spreadsheet exercise. And that exercise will demonstrate and model much of what we cover in the first part of this module. So with that said, why don't we begin? Conservation biologists are oftentimes concerned with the fate of individual species. So oftentimes threatened and endangered species are the focus of conservation efforts. Tigers, for example, snow leopards, and so forth. But oftentimes we do know that the focus of conservation is on protecting groups of species or whole assemblages of species, which we might call biodiversity. And certainly biodiversity conservation has had some importance in the conservation movement and has really been an emphasis in the last couple of decades, you might say. So why is that? Well, certainly we have had a tremendous impact on natural landscapes, humans of course. And that impact has been, quite varied, and oftentimes what we tend to do is fragment landscapes. So we take continuous landscapes and we carve them up in various ways. We build roads, suburban, urban developments, and so forth. And when we do that, we take this nice continuous forest, you might say, and really carve it up into a variety of parcels. And those parcels in many ways represent islands. They represent islands of habitat that are surrounded by a sea of perhaps inhospitable land, inhospitable to those species that normally would live in this type of particular forest, let's say. So in order to better plan for development, to perhaps better mitigate the effects of fragmentation, one strategy is to really try to understand the relationships between species richness, or the number of species in a particular area, relative to this islandizing effect, right? So species richness and islandization. It gives us a means of perhaps dealing with this issue of fragmentation. So what do we know about species richness and islandization? Well, certainly we know that the number of species does relate to area, right? So larger areas tend to have more species than smaller areas. And that's sort of a given. And we know that from really many studies and really basic biology. If you think about perhaps Central Park in Manhattan, big natural area, sort of a natural area. Certainly there are a good number of species, more species in Central Park than you might find in a small neighborhood park elsewhere in Manhattan. So there is a relationship between species richness and area, and that's a positive relationship. So what other factors might contribute to species richness, or the number of species we might find in an area like an island? I'm sure you could think of many, right? There are lots of different things, but the basic framework for understanding that relationship is this equilibrium theory of island biogeography. And the equilibrium theory of island biogeography was really developed and popularized by two people, Robert MacArthur, who some of you might be familiar with, the American ecologist, who was really a pioneer in terms of community ecology, and of course Edward O. Wilson of Harvard University. The basic idea with equilibrium theory of island biogeography is that the species richness we would see in a particular area, like an island, and when I say island, I should clarify that that doesn't necessarily mean a parcel of forest that's surrounded by urban and suburban development like Central Park in Manhattan. An island could also be, for example, a mountaintop or a pond, or actually a proper island somewhere in an ocean. So there are, of course, natural islands as well. And so the basic idea is that the richness we find on these islands is a balance between the immigration of species, so those species that are coming from elsewhere and landing on the island, and the extinction, the recurring extinction of species that are residing on that island. So there's this sort of balance, this interplay between colonists, new species that are arriving, and species there that are going extinct. And so we can make some statements about what we expect in terms of species richness based on those two characteristics. So we can predict, if we know something about immigration and extinction rates, we can predict species richness at something called equilibrium, or an equilibrium state. And this equilibrium state is similar to the equilibrium we've talked about in previous modules. So think back to the metapopulation model, for example. It's the same basic idea. And that is, in an equilibrium state, we expect that the number of species, that species richness will remain unchanged. It's basically stable from one time period to the next. So that might be 1 year to the next, or whatever our time frame is. So an equilibrium state implies that there's some stability, there's some unchanging nature to where we're at. And that equilibrium state really comes when you strike a balance between immigrations and extinctions, now of whole species, to that particular island. And we can make, again, some predictions about what the equilibrium state might be if we know something about those two factors. So in this module, we will build really a model, a mathematical depiction of this equilibrium theory of island biogeography. And the model will look at that balance between immigrations and extinction relative to species richness. And we'll bring in two other factors as well that I think are quite important and central to the whole notion of island biogeography. And that is the effect of area, right, the size of an island, as well as the effect of isolation. So how far removed that little island might be from a mainland or another island, let's say. So area and isolation are important. So we're going to build a basic model. We'll run through some of the tenets of island biogeography and the theory of island biogeography. We'll look at this equilibrium state. And then again, my colleague Terry will come in and really demonstrate this more thoroughly using a spreadsheet exercise that I think will be really helpful for you. So let's start by looking at an example, and let's focus on an actual island. So let's imagine an island, a hypothetical island. Let's say a nice, lovely island off the coast of Central America, somewhere in the Caribbean. Let's say it's off the coast of Honduras. So we want to estimate what we expect species richness to be like. And we know that that's really a balance between immigrations and extinctions, as we've talked about. So how can we capture that sort of mathematically? Let's introduce a couple of terms here. I'm going to introduce two terms. The first one here is called lambda S. So that's the number of species, right, as a subscript to lambda. So that's the number of new species colonizing an island per some amount of time. So this represents the immigration side of things. The next term then is this term mu, and mu will also have a sub S. And that's basically the number of species on an island that's also going extinct per some unit of time. And we want to find the balance between the two. So this is going to represent our extinction side of things, and this will represent our immigration side of things. So on this island, on this nice island off of Honduras, what would we expect equilibrium to be like? Really, equilibrium is this balance between immigrations and extinctions. And so we can write a simple expression to capture that. And the left side of that expression is this term here, which looks a little complicated, but all it's basically saying is that the change in the number of species per amount of time, so this is a rate of change measure, and again we'll call S the number of species on our island, is our rate of immigration minus our rate of extinction. And that should make sort of sense to you, right? If you've got more immigration than you've got extinctions, then your island will be increasing in terms of its rate of change from one time period to the next. And the opposite would be true too. If you've got more extinctions than you've got immigrations, then you would find the island on a negative trajectory. It would be losing species over time. So I hope that makes intuitive sense. So we can use this as a basis for estimating at equilibrium what we expect species richness to be. So we're going to refine these terms a little bit more, and I'm going to show them to you graphically. Let's start with the immigration side of things. And if you see up here in the corner, I've got lambda s, so that indicates that we're dealing with the immigration side of things. And I've drawn a graph here that's got rate, so this will be our immigration rate on the y-axis, and then we've got number of species on the island, s, here on the bottom side of the graph. So let's say that we have an island that we're our island of interest, and let's say that that island is completely denuded of species, right? Some hurricane or tidal wave came through and there's really no species left on that island. What would we expect in terms of immigration rates in that circumstance? What would our maximum rate of immigration be like? Well, our maximum rate of immigration would occur during that period in which there are no species. Because the island is completely open, there are no other competing species, it's free and open, lots of niche space, so we'd expect that our rate of immigration would be relatively high. So I'm going to put this term here, I, and I will be our maximum rate of immigration. Okay? So we would expect our immigration rate to be relatively high on an island now that has no species. And over time, as species start to accumulate on that island, right, we start cramming more and more species on that island, then it's very difficult for new species to arrive and to become established. There's just not enough niche space that's open. And eventually get to the point where we really can't take any more species. So what sort of graph would we expect? What sort of relationship then would we expect between immigration and number of species on our island? Well, we'd expect it to sort of drop down, and we're going to assume a linear relationship in this direction. And eventually we get to this point. Well, what defines that point? That brings in another term here, and we're going to call this term P. And P is just a measure of the number of species that come from our mainland area. So we can only receive species from our mainland, which in this case is Honduras. And we know that Honduras here only has a certain number of species of whatever taxa we're interested in. So once we reach P, there simply are no more species that can immigrate to our island. We've got them all, right? So P is the number of species that could potentially be immigrants. It's the number of species from our mainland, which we might call our source pool. So this is what we'd expect our relationship to be like for immigration. The relationship between immigration and number of species on an island. Now, we can define this line mathematically. And you might recall from some of your early math courses the equation for a line. So if we want to mathematically describe it, the equation is y equals a plus bx. You remember that equation? So the a term represents what? The a term represents the intercept. This is our y-intercept. And the b term now represents what? That represents our slope. So that's the slope of our line, and our slope is the measure of, again, if you recall, our rise over our run. And the x term here relates to our number of species down here. So let's define this mathematically. We've got here a being our value of I, and our slope being what? It's a measure of our rise, which is I over our run, which is p. And we know that this slope is going in a negative direction, so this is actually a negative value, times s. So this equation mathematically describes this line, this one here. Okay, so let's hang on to this one for just a moment, and we'll switch now from the immigration side of things to the extinction side of things. So now we're dealing with extinctions, and we've got the same graph, so now we've got a measure of rate on the y-axis. We'll call this extinction rate, and then we've got number of species on the island, again on the x-axis. So for an island that has no species, what would we expect our extinction rate to be? Our extinction rate here would be 0, right? I mean, if there are no species on an island, no species can go extinct. Now, if on the other side of the spectrum, when we're at P, in other words, we have received all the species we can from the mainland, when we're in that position, we'd expect our extinction rates to be much higher. In fact, we'd expect extinction to be at its maximum point. So E here will represent our maximum extinction rate, and that will occur when our island is fully saturated. We've got the most amount of species. We'd expect at that point more extinctions per unit of time than if we were at the other side of our graph, sort of down in here, where we have very few species. So we can depict now that relationship, so between extinction and number of species on an island, that would look something like this. And as we've done before, we can describe this line mathematically. So the equation of our line is a plus b times x. So our intercept is what? Our a term happens to be 0. So we would write that then as 0 plus our rise over run, which is e over p times x, which happens to be our s term. And remember now that our slope is positive, so we would have a positive value here. So this equation now gives us a means of better quantifying or better expressing our mu term. So this is the extinction side of things. So let's return to our equation, right? The original equation that we started with, in which we've got the rate of change in the number of species on an island per time being really a function of our immigrations and our extinctions. But now that we've sort of further defined these two terms, we can take those new expressions that we have and substitute them into our equation. So let's go ahead and do that. So for the I term, we had what? We had our immigration term, rather. We had I minus IP times S. And now we have minus, right? Our mu term, which was E over P times S. Got it so far? So here we just simply have substituted our equation for our immigration line in here and our equation for our extinction line in here. So why might we do this? Well, if we make these substitutions, then we can use this new equation to estimate species richness at equilibrium. Okay? So we can estimate species richness at equilibrium. So the number of species on the island we expect to be consistent from one year to the next. In other words, when we have no change in number of species. And that, again, is a function of a few things. It's a function of our maximum immigration and extinction rates, as well as, right, the number of species that could come from our mainland source area, so the maximum number of species occurring in our source pool. So here's the same equation, and in order to estimate that species richness at equilibrium, what would we do? Well, we've got our equation, and we've got the left side of our equation that, as you recall, represents the rate in change in the number of species per time. So if we want to estimate equilibrium, we just simply set this side of the equation to 0. If we set that side of the equation to 0, then on the right side of the equation, we are basically trying to solve for S. We want to know the number of species that would occur at an equilibrium state when there's no change from one time period to the next. So there is a bit of algebra in order to do this. You're just simply solving now your equation for S, and I'm going to assume that you can do that on your own. But it's a relatively straightforward calculation, and it ends up giving us here a new term, which is the following. The number of species that we would expect at equilibrium, and to represent that, I'm going to put a little hat on top of S. So number of species at equilibrium, the equilibrium is represented by this little hat, S hat, is now the immigration rate times the number of species in our mainland source pool divided by immigration rate plus extinction rate. So this is our new expression that allows us to solve for equilibrium. What does that look like graphically? There are lots of letters here and mathematical symbols and so forth, but graphically, what does that look like? So this now is a graph of both our immigration and extinction lines, our curves you might call them. And the point at which these two things cross is our equilibrium point. That's our equilibrium number of species. That's our S hat. In other words, we have a balance between immigration and extinctions. So the number of species arriving at the island is offset by the number of extinctions occurring on the island, and in other words, the richness of species remains the same. So this is our equilibrium point that's sort of shown graphically here. And we can put a couple of numbers in there just to demonstrate this equation. So here's our S hat equation, which is I times P over I plus E. And let's say we know that our source pool has 30 species, and through other studies we're able to determine that our immigration rate is 6 and our extinction rate is 4. So we can plug those values into our equation. So that would give us 6 times 30 divided by 6 plus 4. And that ends up giving us a value of 180 in the numerator and 10 in the denominator, so 18. In other words, at equilibrium, given these conditions here, we would expect a total of 18 species. So from one period to the next, we would expect 18 species.